Now shuffle 10 involves an even up jog as well. So if we begin with our original packet of 8 cards that have been clearly numbered so that we can keep track of the individual positions of these cards, performing the even up jog, so that's the same as the last shuffle, shuffle 9. This time we strip these out, but we stack right on top of the left. Well, what does that give us for our new ordering? We get a 1, 3, 5, 7. Sorry, I'll move that over. 2, 4, 6, 8. And with a little bit of thought, you probably could have anticipated that that would happen. We've just switched the 2 halves that we had earlier after shuffle 9 was applied. Okay, so if we write the Cauchy 2-line notation for our permutation, we obtain the following. 1, 3, 5, 7, 2, 4, 6, 8 is the new ordering. That can be converted to 1-line notation, in other words, cycle notation. So 1 is a fixed point, 1 goes to 1. 2 gets sent to 3, 3 gets sent to 5, and 5 gets sent to 2. So it wraps around. So that completes that cycle. It's a 3 cycle. Similarly for 4, 4 gets sent to 7, 7 gets sent to 6, and 6 gets sent to 4. So it wraps around. So that's a second 3 cycle. And then we have just one more fixed point. Whatever's in position 8 will stay in position 8 regardless of how many times you perform that shuffle. Okay, so that's kind of fun. So positions 1 and 8 are fixed points. And then all of the other cards in the middle are kind of moving around among themselves in some fashion. In fact, in the way that we've just listed here. Now, if we color code the position values, we obtain the following. Remember, position values 2, 3, 5, 8 are color-coded red. Position values 1, 4, 6, 7 are color-coded black. So we can readily see that inversion does not occur. So the cards that originally began in positions 1, 4, 6, 7 stay somewhere in that set of position values. Similarly, for cards that originally began in positions 2, 3, 5, 8, stay within that set of position values. And that's what we've written here. So relating this to our Bessey sequence involving zeros and ones, since inversion does not happen, if we perform this shuffle, we'll get exactly this form back. In fact, why don't we just quickly show that? Okay, so we're going to do an even up jog. So you push forward the even position cards, strip those out. Now we're stacking right on left. So the claim is that we'll get back to the form 1, 0, 0, 1, 0, 1, 1, 0. Okay? Now it is true that the ones are moving around among themselves except for one of them. Can you think through which one is going to stay exactly where it is? It's the first one, right? Remember, we have 2 fixed points. Whatever's in position 1 stays in position 1. Whatever's in position 8 at the beginning stays in position 8. Similarly, for the zeros are being permuted among themselves with the exception that the last 0 here, which is in the 8th position, stays exactly where it is, or in other words, gets returned to its original location. And if we look at our graph here, top row on the right, this is the Bessey shuffle diagram that goes with an even up jog in which we stack the right pile on top of the left. We can see our fixed points right here, 1 and 8, they don't go anywhere. And then 2, as we can see here, gets assigned to 3, gets sent to 3, 3 gets sent to 5, 5 gets sent back to 2. So we have a little 3 cycle. We also call that an orbit. And then if we go to 4, we see that it's sent to 7, 7 is sent to 6, and then 6 is sent to 4, completing that 3 cycle. And that's also an orbit. Those values are just moving around among themselves according to the direction of the arrows in the diagram. And notice this time we're looking at a shuffle that has order 3. Now when we say a shuffle has a certain order, what we mean by that is you need to apply that shuffle that many times, the order number of the shuffle, to return the packet to its original order. Okay, so since we're looking at a product of 3 cycles over here, that means performing this shuffle 3 times resets the packet to its original order.